Hello friends, welcome to another lecture on Inside Classes. In this lecture, we will discuss about special cases of Routh Hurwitz criteria, which is a zeroth row in the RH table. Now let's move forward to second special case of RH criteria where there lies a zero row in RH table, that is all the elements in a row are zero. Now before taking example for this special case, we need to understand that such special case occurs when there are symmetric poles in the characteristic equation. Now these symmetric poles can be of three types. As you can see in the figure, the first one is when there are symmetric imaginary poles and it is symmetric about the origin. In the second case, there are four poles and each poles are in each quadrant and they are symmetric about the origin. In the third case, there can be real poles which are on real axis and they are symmetric about the origin again. Now for these two cases, that is case second and case 3, we will get sign change in the first row of our RH table, and from there we can directly conclude that these systems are unstable. Now for the case when there are imaginary poles on the imaginary axis symmetric about the origin, we will not get a sign change in the RH table. So for this system there lies an additional step in which we will have to factorize the auxiliary equation. What is auxiliary equation? We will see in our examples. So when we factorize these auxiliary equations, we have to see that whether we have a repeated roots or not repeated roots. When the roots are not repeated, then the system will be stable. But when the roots are repeated, then the system becomes unstable. So we have to remember in RH criteria, then when we get a row with all zero elements and we do not get a sign change in our first column, then we need to factorize the auxiliary equation and see whether there are repeated roots or not. If there are no repeated roots, the system will be marginally stable. If there are repeated roots, system will be unstable. So let's take an example for this special case. Here you can see that this equation does not satisfy any of the prior conditions of RH criteria. That is, there are no missing powers of S as well as there is no sign change. So we have to go to the fourth condition and we have to calculate the RH table. Now when we calculate the RH table, we can see that there is a row with all zero elements, because of which we cannot move forward and calculate values for the last row. In this case, we will take the auxiliary equation of the row just above a row with all zero elements. In this case, since S1 has all elements as 0, we will take auxiliary equation from S square row. So for constructing auxiliary equation, we will take the row just above the row with all elements 0. In this, with the first element, we will multiply the power of S that is on the left side of this term. So here we have 5 and on the left side we have S square. So we will multiply 5 by S square and then we will reduce the power of S by 0 for the next element. Here, since we have S square, we will reduce it by 2, so we will get S raised to power 0. So our auxiliary equation becomes 5S square plus 30 equal to 0. We will differentiate this auxiliary equation by S and we will get these corresponding values 10S plus 0. We will use this equation to populate the next rows. So for S raised to power 1, the coefficient is 10. We'll put that value here. For the next value, since it is 0, we will be populating 0 here. Now using these terms, we will move forward with our calculations and we will complete the RH table. We have completed our RH table and we can see that there are no sign changes in the first column. But remember, when there is row with all zero elements and there is no sign change in the first column, we need to factorize the auxiliary equation. During the earlier part, we have constructed the auxiliary equation which was 5s square plus 30. So we will factorize it. So we will get s equal to plus minus j root of 6. Since we can see that there are no repeated roots here. That is why we can conclude here that the system will be marginally stable. In the pole zero plot as well as the step response curve, we can see that there are poles on the imaginary axis as well as the step response of the system is oscillating. Hence the system is marginally stable. Let's take another example for same case. Here we will have a slightly higher polynomial. We will construct the RH table as we did earlier. Now here for s raised to power 3 row, we will get all zero elements. We will construct the auxiliary equation in the similar manner that we calculated earlier. Again, we will use the row just above the all zero element row. So here the first coefficient is 2. We will multiply this 2 with the power of s just left to that. So that is 2 s raised to power 4. Now for next term, we will reduce the power by 2. So it will be s square. So 4 into s square will be the second term. And again, we will reduce the power of s by 2. That will be s raised to power 0. So we will get our auxiliary equation 2s raised to power 4 plus 4s square plus 2 equal to 0. We will differentiate this equation and we will get following term. We will replace the coefficients of the differentiated auxiliary equation in the all zero element row, which will be replacing 0 0 by 8 8. But here we can see one thing, that in both elements 8 is common. we can take the common value of 8 out and we will be left over with 1 1, which will be easier to calculate. Similar such thing we could have done in the s raised to power 4 row, where there is 2 common in all the 3 terms. We could have taken 2 out of them. We would have 1, 2 and 1 as the terms in our s raised to power 4 row. We will proceed further with the calculation using those terms. Again, the next row, 2 can be taken as a common factor. Moving forward, we again get a row with all 0 elements. We will again construct an auxiliary equation based on the row just above it. So here the auxiliary equation will be s square plus 1. We will differentiate this auxiliary equation and use the equation obtained by differentiation to populate the values of all 0 element row. So here we can see we have replaced those values by 2 and 0. And we will proceed further with the calculation. Having completed all the calculations, we can see that there are no sign changes in the first column of the RH matrix. However, there were 2 rows with all 0 elements. So there are 2 auxiliary equations and we will need to factorize them. The first auxiliary equation was 2s raised to power 4 plus 4s square plus 2 based on this row. Since it is a power of s raised to power 4, we will assume that s square is equal to y. Substituting s square by y, we will construct this equation and we will factorize it. So we can see that here there is a repeated root y equal to minus 1 and y equal to minus 1. We will replace the value of y by s square. Again, we will take the root of factors. So we will get our roots as minus j, j and j. We can fairly see here that the roots are repeated. From here, we can directly conclude that the system is unstable. Just for completing the procedure, let's even calculate the value of second auxiliary equation. Here we can see that this auxiliary equation has again roots at minus 1 and j. So we can see that the whole system has repeated roots, and from here we can conclude that the system is actually unstable. So remember, whenever there are repeated roots, the system will be unstable. We will see the pole 0 plot as well as the step response plot for this equation. In the pole 0 plot, we can see only 3 poles. However, for the minus j value, there are 3 poles, and for the j value, there are 3 poles. So these poles are overlapping, so you cannot distinguishingly see them here in this pole 0 plot. When we see the step response curve, we can see that the response is oscillating and it is constantly increasing in its amplitude. Hence, it is an unstable system. For further understanding it better, let's take another example for same type. Here we will populate the RH matrix. We will calculate the auxiliary equation, replace the all 0 element row with the equation obtained by differentiating the auxiliary equation. After completing the calculations, we can see in the first column there are actually 2 sign changes, which implies that there are 2 poles in the right hand side of the imaginary axis. And from here we can directly conclude that the system is unstable. But let's factorize the auxiliary equation here as well to see what kind of poles we get. We can see that the poles are symmetric about the origin, and there are 4 such poles. We will see the step response as well as pole 0 plot for this equation. Now here you can see there are 6 poles in the pole 0 plot and 4 of them are symmetric. These 4 poles correspond to the auxiliary equation which we calculated. From the step response we can see that the system is unstable as the amplitude of the response increases to a very high value. If you liked the video, please subscribe the channel and share it with your friends. Thank you.